Welcome to The Explainer. So today, we're setting the stage for a really deep dive into the hidden physics and, honestly, the high-stakes math behind modern medicine. I always kind of just assumed the machines did all the heavy lifting, right? But it turns out, behind literally every single successful treatment is this invisible, incredibly complex world of mathematical modeling. We're going to decode the exact algorithms that make modern radiation oncology actually possible.
Okay, let's dive right into this. Here is the central problem, and it's a massive physics puzzle. How do you know what's happening deep under the skin when you literally cannot look? Think about it. We can't safely or practically stick a dosimeter directly inside a patient's tumor to measure the absorbed dose during their actual treatment. We just can't do it. So, because direct measurement inside the patient is impossible, we have to rely entirely on calculations. Here's our roadmap for today. We'll start with the high-stakes math. Then we'll look at the transition from water to humans and decode the dose components. After that, we'll crack open kernels and convolution, and finally, we'll wrap up with the ultimate speed versus accuracy battle.
All right, Section 1, the high-stakes math and the dilemma of accuracy versus speed.
If we look at the evolutionary timeline of these calculations, you'll see this really fascinating trend. It's basically a technological arms race. And why does this race matter so much? Well, accurate 3D dose calculation is absolutely the foundational center of modern radiation oncology. It is literally the only reliable link between the treatment parameters we punch into a computer and the actual clinical outcome for the patient. I mean, if the math is wrong, the treatment is wrong. Back in the 1940s, physicists were essentially flying blind, relying on hand calculations like the Clarkson method. By the 70s, we moved to slightly more complex manual and early computer models. But then, look at the explosion from the 1980s onwards. We start seeing model-based algorithms and Monte Carlo methods totally taking over, leading right up to the 2010s with things like Accurus XP. It's just amazing to see how our ability to map radiation inside the human body evolved from these crude approximations to stunningly precise physics simulations. And it tracks perfectly with the rise in computer processing power.
Moving on to Section 2, from water to humans, evolving the algorithms.
To really appreciate where we are today, we kind of need to understand how early methods handled the human body. For a long time, we relied on what were called correction-based algorithms. We basically treated the human body like a giant, uniform box of water. Imagine that. Physicists would literally measure dose distributions in a water tank, called a water phantom, and then they'd use math to extrapolate those measurements to a patient. They'd just apply corrections for the patient's curved surface or different tissues. But then model-based algorithms came along and completely flipped the script. Instead of relying on a box of water, they calculate the dose directly inside a digital representation of the patient. They do this by explicitly modeling how energy transports through matter. We stopped correcting water measurements, and we started actually simulating the physics in human tissue, a real game changer.
Section 3. Decoding the dose components and breaking down the beam.
So a clinical photon beam isn't just, a simple laser pointer of energy. When radiation hits a patient, the resulting dose is this cocktail of different interactions. About 70% of the total dose comes from the primary dose. That's the direct, unscattered photons. But a whopping 30% comes from the phantom scatter factor. That's radiation bouncing around inside the patient's own body. And here is a genuinely surprising fun fact for you. Another 5 to 10% comes from head scatter. That is literally radiation bouncing off the internal components of the treatment machine itself before it even reaches the patient. Crazy, right? And this brilliantly illustrates what we're talking about. It's this intricate tree diagram, tracing the life of photon radiant energy. The exact moment it exits the machine's target, it splits. You can see how non-interacted photons enter the patient and immediately divide into primary dose versus scatter. It shows us that to calculate the final dose accurately, our algorithms have to track not just the main beam, but all these secondary, bouncing, energetic particles, including bremsstrahlin and annihilation photons. It is just a chaotic cascade of physics that we have to perfectly predict. All right, Section 4, kernels and convolution, the real engine of modern therapy.
It all starts with a concept called TERMA, which stands for Total Energy Released per Unit Mass. Think of TERMA as the raw initial energy drop. It's the exact moment the photon hits, before that energy even has a chance to spread out into the surrounding cells. When a primary photon beam enters the body, it interacts with tissue and releases energy to secondary particles, and TERMA is simply the measure of that specific initial deposit.
But, as we know, energy doesn't just stay where it's dropped, right? It spreads.
And that is exactly where dose kernels come in. A dose kernel is a mathematical description of exactly how that energy spreads from the primary interaction point. If Terma is dropping a heavy stone into a perfectly still pond, the kernel is the specific shape and size of the splash and the ripples that travel outward. We use different types of kernels, like point spread, pencil beam, and planar, depending on exactly how we want to calculate that physical spread of energy in a medium.
You can really see the difference here. On one side, notice the point spread kernel. This is that 3D teardrop-shaped spread happening around a single interaction point. But then over on the other side, the pencil beam kernel takes a totally different approach. It describes how energy spreads from a narrow, monodirectional beam tracking downwards into a semi-infinite medium. Pencil beams were incredibly popular for a long time because they allowed computers to calculate doses way faster by collapsing some of that complex 3D math into a much more streamlined shape.
So the crucial point is how this all comes together in convolution. We mathematically multiply the incoming radiation, the fluence on the left, with our point kernel in the middle. Fluence multiplied by the kernel equals the final dose on the right. Basically, we are just superimposing millions of those tiny little splashes across the entire volume to get our final cumulative dose map. It's like a giant puzzle.
Of course, the human body isn't homogeneous, is it? It's a hugely diverse landscape of different densities. You've got incredibly dense bone, soft tissue, and airy lungs. So to calculate TIRMA accurately across this varied terrain, the algorithm scales the distance the photon travels based on the radiological path length. If the beam hits dense bone, the energy is absorbed really quickly and the ripples are tight. If it hits airy lung tissue, it travels much, much further. The algorithm dynamically stretches or shrinks those kernels based entirely on the local electron density of the patient's specific anatomy.
Section 5. The speed versus accuracy battle, the ultimate trade-off.
Now we reach the absolute gold standard of all dose calculation, the Monte Carlo method. Instead of using generalized kernels and convolutions, Monte Carlo explicitly traces the individual histories of millions and sometimes billions of individual photons and secondary electrons as they bounce through matter. It uses pure physics probabilities at every single interaction point, so it offers virtually perfect calculation accuracy. But you might be wondering, why isn't it used for absolutely everything? Well, because it's kind of like trying to perfectly predict the exact path of a billion pinballs bouncing around inside a machine simultaneously. It is incredibly accurate, yes, but it drains a staggering amount of computing power.
Now, what's really interesting about this is how it creates the ultimate trade-off in medical physics. It's your classic rabbit and tortoise scenario. On one hand, the pencil beam algorithm is our rabbit. It's fast, allowing doctors to plan treatments super quickly, but it definitely sacrifices accuracy, especially in complex areas like the lungs. On the other hand, Monte Carlo is our tortoise. It hits the absolute bullseye on calculation accuracy, but historically, it was just far too slow for routine daily use. The superposition and convolution models sort of sit right in the middle, trying to offer the best of both worlds.
Which leaves us with a final, really provocative thought. As we look at the trajectory of our computational capabilities, CPU and GPU power is growing exponentially. So what happens when we reach a point where computational power is virtually limitless? What happens when Monte Carlo algorithms run as fast as pencil beam algorithms? When we no longer have to choose between speed and accuracy, we are going to enter a totally new era of personalized medicine where the math is perfect, the calculation is instant, and the patient outcomes are better than ever before. Thanks for joining me on this explainer, and next time you see a medical machine, remember the invisible universe of math running just beneath the surface.